guys feel today? Tired and ready for summer? No, absolutely fair. We're getting there soon, though. Okay. Brief summary of events. The Waves homework assignment is live. It's just a homework assignment so that you can access it and look at it over the week without having to worry about it having a quiz timer. It's very, very short, just something to apply a couple of the formulas and facts that we talked about this week. Just like 4 questions just to have looked at before the end of Friday is all. I have also been updating Brightspace a bit. Oops. I'm planning, turns out I haven't actually uploaded them yet. I have prepared exam practice questions and a list of exam concepts that will go live on Brightspace today. It was my intention to have made them already. It was my intention to upload them by now. I apologize. But those will be there, and this week and next week, if at any point, we will definitely go over that list of things together and probably look at some practice questions as well. I will also put up an answer key for said practice questions, as I usually do, for you guys to be able to use as review. I'm doing this really quickly so that it's up before I forget. Because I have the memory span of a goldfish. Okay. Brightspace, scroll down. The Waves notes are also active for you to peruse. And final exam tab, we have practice questions. Again, about twice the length of a normal test. And the topic list. Everything summarizing the things we have discussed over the semester that will be on the exam. Those are all there. We will review this a little more in detail possibly after today. I want to at least talk about these last 3 things. I'd like to do that today. So, before we move on to that, does anyone have any questions?
When is the final exam going to open next week? You know yet?
When will it open? Oh, exam season officially begins next Friday. So it'll open then, and then it'll run through. I think there's exams till, I know Tuesday, possibly Wednesday. Let me check because that information is not in my brain. As many times as I have to come back to the academic calendar tab to look at what days we do and don't have off, and also the exam schedule, you'd think my computer could just get to it faster, or I would just keep the tab open. Okay, spring. Exams run through Wednesday, May 12th. So you'll need to have it finished by midnight, Wednesday, May 12th. Thank you for asking, because now that information is in my brain. Okay. So, any... Well, that's not good. Good talk. Any other questions before we get started? All right, so we've talked about waves in general. We've looked at things like sound and things like light. Ironically, despite the fact that we see using visible light as the medium through which our eyes function, we've never actually seen a photon. Like, good luck catching a photon and being able to examine it, between the fact that they move too fast and the fact that they're made of fundamentally intangible things. So all of our research about what light is and how it works hasn't been based on looking at the light itself, because you can't. Instead, we just have to look at what the light does when it interacts with things. Kind of like how we can't really define or view energy by itself. We can only see what happens when objects possess energy. And from observing light, and subsequently other types of waves, we have figured out that there are certain things that all waves do when they hit things. Because waves have to or can choose to travel through mediums, they will eventually reach a point where they hit a different medium. So when light from space enters our atmosphere, it will go from the void of space into the air that makes up the atmosphere. That's a change in the medium. When sound waves from my voice travel through the air to hit your eardrum, that's a change in medium, going from the gaseous air to your solid eardrum. Every single time a wave strikes a new medium, something is going to happen. And this is not an exhaustive list, but these are the three main things we're going to focus on that can happen when waves strike a boundary. A boundary simply being defined as the edge of the new medium that the wave is trying to strike and possibly travel into. And you've interacted with all three of these before. In fact, I can almost guarantee you've heard all of them before. Refraction might be the most awkward word up there from a normal vernacular perspective, but you've seen all of this stuff happen. The most obvious thing that waves can do when they hit something is be reflected by it. Every single thing that you see is, well, most things that you can see is due to the fact that light bounces off of that object and then travels into your eyeball. So my blue shirt looks blue because blue photons bounce off of it, enter your eye, trigger the blue photoreceptive cells at the back. Most things reflect some amount of waves that strike them. Light, sound, whatever it is. It's very rare that something will not reflect anything. Most things reflect something. And there is a law, a formula, describing a particular aspect of reflection that, again, you've definitely noticed this before. Waves will bounce off of an object at the same angle that they approach. What this means is you need to be looking straight at a mirror to successfully see yourself in that mirror. If the board is a mirror right now, and my wave light bouncing off of me approaches it at a 90-degree angle to its surface, it'll bounce back off at a 90-degree angle and come to my eye. But if I'm standing here and the light from me bounces off, approaches at a 45-degree angle, it'll bounce off at a 45-degree angle. So light from me would bounce over there, and I wouldn't end up seeing my reflection. Which is why we can use mirrors to both look at ourselves, but also angle them around to see other things, like your rear view mirror. Fun fact about your rear view mirror, though, you've probably noticed, but have begun to selectively ignore, the text at the bottom that says objects in mirror may be closer than they appear. The reason for that is, if you're here driving and the mirror is here off attached to the door and there's another car back here, if you were to physically turn around to look at that car, there would be that much distance between you and the car that the light would have to travel. But if you look at the mirror, the light bouncing off of the car, hits the mirror, then enters your eye. That light has to travel a longer distance to actually hit your eyeball. That's why it looks further away. The light traveled further, even though the car is the same distance. And this is one of many reasons why mirrors are tricky. So that's why that happens. This particular principle, just this formula of angle in equals angle out, is called Snell's law. It's just this simple. Angle in equals angle out. All objects, okay, most objects, there are a few exceptions, will reflect some amount of light, even if they don't look like a mirror. There is a scientific molecular difference between whether or not you can actually see your reflection in something, and it has to do with the surface of the object in question. Molecularly speaking, pretty much every object is bumpy when you get down to the atomic level, but the smoother something is, the better light is able to reflect off of it. If you're shooting a bunch of rays at a completely flat surface, all the incident rays are at the same angle, then Snell's law says that the rays reflected back will go away at the same angle. And if the surface is flat, that better facilitates all of them going off in the same direction. And that's when you can actually see the image. If there's an object here, all the light needs to hit this and bounce off at the same angle so that the image itself ends up over there. This is mirrors, shiny objects. If something is actually able of producing a reflection, it is, atomically speaking, a very smooth and polished surface, which is why mirrors are such a pain to make, and they usually involve some layer of liquid. Most everything else in the universe, like the tables, the cinder blocks, most clothing, is not very smooth, molecularly speaking. It has a very bumpy surface, which means that even though every single incident photon is coming in at the same angle, they're all hitting different angled parts of the object. So they're all going to bounce off in different directions anyway, destroying the image. There won't be an image formed because they're all moving away in different directions. So when you look at any given cinder block, the photons coming at your eye could have come from anywhere in the room.
Do you mean like with the mirror thing, like there's liquid like over the mirror? Or like what do you mean it's made with liquid?
There is not actively liquid inside of the solid mirror. At least historically, we don't have to do this all the time these days, but historically mirrors were made by taking the glass, coating it in a reflective liquid, usually mercury, unfortunately, sometimes silver, and spinning it around very fast to evenly coat the surface with that material, then solidifying it and sealing it in. Similar to how, and this creates a smooth surface similar to how water is pretty much always a smooth surface when it's still water and you can see your reflection in it. That's not the primary tactic used to make mirrors anymore, but the principle is still similar. There's a layer under the glass that is actually the reflective part, because transparent glass by itself doesn't always form a very good reflective image. Like, I can see myself in my window, but I can see through my reflection. So the glass itself is not the actual mirror, there's a layer under the glass. And tragically, that layer used to be toxic mercury. Occasionally silver, which you also don't want to ingest. Fun fact though, the fact that mirrors were made of silver is why vampires don't have reflections. Silver, like, there's the silver bullet thing for werewolves, but it seems as though, mythologically speaking, most of those types of monsters had a silver weakness. Silver was just a holy metal, I guess, like connected to the light of the moon. So, because it was like holy, vampires couldn't see themselves in silver mirrors. Similarly, most photographs were developed using silver nitrate. So there was silver involved in that process, which is why vampires also wouldn't appear in photos. Except these days, most mirrors aren't silver, and most photos, at least digital photos, have nothing to do with silver nitrate. So there's a couple text posts online about, imagine a situation where you are a vampire, you have not seen your photo or your reflection in centuries, all of a sudden you walk into the first bathroom that doesn't have silver mirrors and you see yourself for the first time in millennia.
Is there also like the reason why like two-way mirrors? Because like those are different. Like you can see it, but the other person can't see it.
That two-way mirrors are double act between reflection and refraction. You can create it, well, to be honest, most objects don't reflect every single wave that passes through them. Not all the light that hits my shirt is going to immediately bounce off of my shirt, because if it did, my shirt would be probably as bright as the lamps above. Some of that energy actually goes into the objects in question, which is why some things appear duller or darker than other objects. They don't reflect every single photon. And in the case of a two-way mirror, some of the light that doesn't bounce off travels through the glass unimpeded, which is usually why a two-way mirror looks, like if you're on the side where you can see through it, it usually looks like duller than reality because you're not getting every photon you could be getting. So, this is why not everything is a mirror. There is the terms for this. If the mirror is flat and you can see an image in it, we call that a specular reflection. Specular, kind of like spectacle. Meanwhile, the bumpy kind is a diffuse reflection because the photons become diffused and don't form an image. One more quick thing about mirrors. Kind of ties back to the car example. When looking into a mirror, it kind of, don't worry about the formulas, we're just focusing on concepts for right now. When looking into a mirror, it kind of appears as though your reflection is some physical distance inside of the hypothetical mirror space. As you draw closer to the mirror, it looks like your reflection draws closer to you. That's because what you're seeing is a hologram, basically. And yes, the light bounces and acts as though it travels some distance into the mirror to form the hologram. Which is, again, why this happens. The theoretical car is this distance, like the hologram car that you see is this distance into the mirror, but then that light still has to travel this far after that to get to your eye. So it looks, again, even further away. Okay. So reflection was the first boundary interaction that we're going to look at. The second is a similar sounding word, refraction. This one, you have definitely interacted with it. Maybe you haven't consciously ever noticed it, or maybe not at least thought about it, but trust me, this happens all the time. Say, for example, you're out at a restaurant, you have water, and for the sake of this being easy to see, imagine your water has no ice in it, and it's a clear glass. You put a straw in it, and you notice it kind of looks like the straw under the water is displaced a little bit right or left from the actual physical straw itself. You might have also noticed this, like getting into the pool, where you look down, and it kind of looks like your body is either shifted to one side or the other, or like it's bending in a different direction. You stick down your arm, and it looks like it bends in a direction you weren't expecting. These sound vaguely familiar? Okay, that is entirely because of this, as evidenced by the pictures up there. Refraction refers to the idea that if light doesn't bounce off of the object, if light doesn't reflect, then it has to go into the object itself. And weirdly, when light enters a new object, it bends. I've mentioned that we assume light operates at the same speed throughout every part of the universe. We do that because on some level the photon itself does still travel the same distance in the same amount of time, and because we kind of need light speed to be constant for most of our math to work. But when light, imagine light going from space into Earth's atmosphere. From the void into air is a boundary. When the light enters the atmosphere, it now has to fight through a bunch of molecules that it didn't have to fight through in space. So that kind of has the effect of slowing it down, but instead of its speed literally reducing, its frequency and wavelength gets shifted slightly, and the wave gets bent. Kind of like it's being partially deflected. Not fully in the case of reflection, but just a little bit, just to the point where it bends slightly and changes the angle that it's going to travel at. And this becomes most apparent when the wave travels back out of that object. Say this is a thin sheet of glass, like a window. Photon comes in. When it enters a new medium, it is going to bend. The degree to which it bends will depend a lot on what the medium it was previously in, then the medium that it is now in. The formula up here, we're not going to spend much time on it because I want to make sure to get through the concepts primarily with you guys. This stands for the index of refraction, and that's how much any given material bends the light that enters it. Every material has a different one. Light enters the glass, light bends, but when light exits the glass, it bends back to its original trajectory. The problem is, the photon is now skipped some distance away from where it should have been normally, which creates that sort of bent, displaced effect in a glass of water. So anytime light enters a new object, it will bend. That is a given. What you're about to see is a very extreme example of that. This man is okay. The refraction has simply shifted his head away by about 2 feet.
Does it also depend on like what angle you look at it?
The angle of perception might not matter as much. Well, no, it would, okay, there is one case where the angle would matter a lot, and that's if the photon is traveling straight towards you. Because the way that the math works is you take this angle here and it gets adjusted into this angle. But if it's straight down, that's the one case it wouldn't really bend. So if the photon was shot directly towards you and it traveled through glass to reach you, or through whatever this is, that part should be fine. That wouldn't get bent. But every other photon adjacent to that one would. So that would be the one part of the visual that doesn't move. Now, there's that same visual. Now this is important for a couple of reasons. In terms of the things that humans need in order to exist, this is the principle that makes lenses work. Light enters the lens, and based on the type of glass that it's made of, the shape of the lens, the light is going to bend. And the purpose of a lens is specifically to bend all of the light into a specific spot. In the case of the human eye and the glasses that we wear over the top of the human eye, every eye already has a lens on it. It's not a glass one, but most of the time the organic one that's already there functions, does its job pretty well. Light enters this eye, it hits this lens, which is a new medium. The lens is naturally curved in such a way to cause all of the incident light to bend and to try to form a hologram of whatever you're looking at right here. And if you have 20/20 vision, the hologram appears perfectly on the back of your eye. The photoreceptive cells in the back of your eye can read what it is you're supposed to see, and that signal gets sent to your brain. This wouldn't happen if our eye didn't have a lens on it. If the light just came in, you'd probably only be able to see in a straight cylinder in front of you. The fact that it is a lens means that a lot more light is able to actually hit the lens, bend correctly into the back of the eye, and get registered properly. That said, if you don't have 20/20 vision, what that mechanically means is either the lens on the front of your eyeball isn't the correct focal length, or your eyeball itself is I don't mean this the wrong way. Your eyeball might be the wrong shape. Because even if your lens is okay, if your eyeball itself is physically squashed, and this happens, I keep forgetting which one's which. Between nearsighted and farsighted, one of them your eyeball is squashed like this shape of egg, the other the eye is squashed kind of like this shape of egg. Either way, that puts the photoreceptor cells back here, but the hologram here. So we add an additional glasses lens on the front of the eye to further adjust this image to where it needs to go. And this only works because of refraction, because there's that new material in front of the eye that causes the light to bend more than the air would. So all lenses function because of refraction. Similarly, all prisms function because of refraction. Is anyone here not familiar with a prism? Okay. So, all light will bend upon entering the new object, but every color of light bends at a slightly different angle, because when you refract, your frequency gets adjusted, and the amount of adjustment depends on the frequency it already had. So different colors of light are going to bend to different degrees, which has the effect of scattering all the different colors and causing them to travel separately. Which is why prisms take normal light that is full of every color of photon and scatters those colors so that they are traveling separately and can be separately seen. Prisms do this, like the physical crystal that you can hold up to the light. Water in the sky does this, and that's how rainbows are formed. The water droplets in the atmosphere, light enters them, the light scatters as it exits them, and then it forms all the different colors. Is anyone here not familiar with the idea that the light the sun gives off is every color photon traveling together in the same direction? Has anyone not heard that one before? Okay.
Is it the same concept with like rainbows? Like is that light? Like after it rains?
Yes. So rainbows, the light from the sun enters the atmosphere. That light is every photon, every color traveling together at once. But when that light hits water droplets after a rainstorm, the water is a new medium from the air, so the water will refract the light, causing the colors to move in different directions, forming the rainbow. And they do refract in Roy G. Biv order. Every color bends at a slightly different angle based on what order they are in the electromagnetic spectrum. So, waves hit something, they could bounce off, they could refract through it and get bent. There's one third thing, and it's kind of the least impressive. The wave could just be absorbed. Waves are traveling energy, and when matter possesses energy, it tends to just warm up. So if we're looking at light specifically, when light hits an opaque object that it can't refract through, it's just going to be absorbed. The energy will be absorbed. Energy of the photon will be taken in and absorbed by the object's matter, and then it'll just be energy inside the object and not a photon anymore. This is why when you go outside on a sunny day, you get warmer. Regardless of air temperature, if you're in direct sunlight, you're going to be warmer than if you weren't in direct sunlight. You are literally just absorbing the light into yourself as thermal energy. Plants are able to take that absorption to a slightly different level than we are, because we lack chlorophyll. But if the energy is absorbed, if it doesn't reflect off and it doesn't travel through, it'll just be absorbed, it'll just become thermal energy. This principle, again, makes things warmer in sunlight, but it also contributes to solar panels, because that's a case where you build a machine designed to absorb the energy and turn it into electricity as opposed to thermal energy. There will still be some thermal energy produced, though. Solar panel farms are famously hot, and because they kind of bounce light off of themselves as well as absorb it, and so they end up forming like a giant column of reflected light. If a bird travels through that column, it will get toasted and die, which is one reason why we haven't built solar panel roads yet, because they'll get so hot that they will kill birds and humans and melt your car's tires. They can, at least. They have the potential to, depending on the panel and how much sunlight you get. So, 3 different things that can happen when a wave hits something. And usually, in the real world, they all happen together at the same time. Very rarely will one of those 3 things happen by itself. Usually, any given object that is hit by light, 2 or more of these will happen at the same time. There is light bouncing off of my shirt, which is why you can see it, but there's also a lot of light being absorbed by my shirt, because the lamps are giving off every color, only the blue is bouncing off of this part, the rest of it is absorbed. In the case of mirrors, unless it's a perfect mirror where you can see a perfect hologram of reality in it, it's going to absorb some energy as well. The two-way mirror is actually a good example. Some light bounces off, some light travels through and refracts. Some light would probably get absorbed too. Very rarely does something not absorb any light. There's also the case, the fringe case, where something absorbs all of the light that hits it. Have you guys heard of Vanta Black?
Isn't that a color? It's really black.
It's less of a color and more of a material that was developed. Most objects, even darkly colored objects that tend to absorb more light, still reflect some light. Like these countertops and the desks are black. Black objects absorb more energy rather than reflect it, which is why less colors bounce off of it. It's also why dark colored cars tend to get hotter in sunlight. They're just absorbing more energy. But most objects still reflect something. I can see a shine on the desk. It helps me know that the desk is there, and I can identify the features of the desk. But scientists developed a material that reflects basically no light, whereas a perfect mirror reflects basically all light. This material that was developed absorbs 99.9% of it. The material itself is called Vanta Black. This is the same statue. One of them is normal, the other is painted with Vanta Black. The human eye was not meant to perceive this. This is the absence of light. Notice you can't even see the features of the statue. It's just a void. And it looks very concerning to the human eye because our eye is predicated on the idea that some light reflects off of everything, and that will help our depth perception. There's no light coming from that. it's featureless. It's like the void of space, which is one reason why scientists have invented this stuff, but you can't buy it commercially, because if this was just able to be used by like car manufacturers and clothing brands, you would create products that A, would scare people on a fundamental level, but B, might cause like actual car accidents if you can't tell how far away something is. Like reaching out into that, you wouldn't know at what point you will touch nose, or you wouldn't know if your hand would just pass straight through it. There was actually legal action taken against a clothing manufacturer that wanted to make clothes out of this stuff. This is like the one time light is pretty much mostly absorbed. The other case would be black holes.
Have we
So,
taken a picture of a black hole?
we do, although not because the black hole itself is very similar to the Vanta black. No light comes out of it. So you can't see it against the darkness of space because, well, that's dark on top of dark. There's no difference there. The only reason we have a photograph of a black hole is because we managed to angle the camera such that the black hole was in front of something bright, which took a lot of doing. The particular NASA scientist who had to do this, she had to take a lot of pictures of a very specific region of space over a long amount of time to get all the pictures that were compiled together into the one image that actually showed it. It took a lot of work. It was and is revolutionary, and science thanks her. We are nearing the end of lecture, and I don't want to keep you guys. I will say, though, the three principles from today, reflection, refraction, and absorption, is the reason why the sky is blue and the grass is green. In movies and pictures from the moon, you notice how when you look up into the sky, you just see into the void of space. Like from the moon landing photos, it's just the void. It's because the moon doesn't have an atmosphere. The light coming from the sun and the stars doesn't hit a new boundary as it goes from the void to your eye if you are on the moon. On Earth, we have an atmosphere. That's a new boundary that the light has to travel into. So when the light from the sun enters that atmosphere, it bends and gets scattered into its colors. In addition, once it's scattered like this, it starts getting absorbed one color at a time. And our sun, like our specific solar system's sun, gives off colors of every frequency, but it's mostly blue. There's mostly blue. Next most common color is probably red, but it's mostly blue. So after the light gets scattered like this, the particles of the atmosphere start absorbing it and eating it one color at a time, which also warms the atmosphere. That's how we get heat from the sun. But the indigo gets completely swallowed, the violet gets completely swallowed, some of the blue gets swallowed, and that's why we get left with light blue as the most prominent color during the day. At sunset, though, the sun has to change what angle the light comes in at, which means there's more atmosphere between you and the actual light. That has the effect of absorbing more of that light. So at sunrise and sunset, the blue gets eaten, as does the green and some of the yellow, which leaves you with the reds and oranges of sunset and sunrise. There's also very little green, like the actual color that a human eye would represent as green, in our sun's light. Green is the color it gives off the least of, which is A, why the sky is never green, At night, it's kind of violet. During the day, it's blue. At sunrise, sunset, it's red, orange. You hardly ever see green sky because there's just no green light the sun gives off. Plants are green to take advantage of that fact because whatever color you reflect, you absorb everything else. Plants are green so that they reflect what there's the least of and they can eat everything else. If our universe just had if our solar system had a different sun that gave off different colors of light, plants would be a different color to compensate. Like, there could be a world out there with a green sky and blue plants, theoretically. So, all that entire lecture today to solve two of those most pressing questions that everyone has asked since they were 3. Blue sky and green plants. I can't answer why dirt tastes good though. Have a good day. We'll meet back tomorrow to answer any more waves-based questions and probably start talking about exam stuff.
I don't think I can make it to lecture tomorrow because someone in our family